Okay, good morning everybody. I hope everyone's having a wonderful day. So last day we talked about big O notation and we've seen some examples of how we could prove big O claims. So we showed that how we could take and prove some complexity function is big O of another complexity function. In addition, we also talked about how you can prove a function is not big O of another function. So we talked about those are two key things. One remark I wanted to make that normally it's something that you just sort of adopt over time, but most certainly I just feel like I want to mention it, is that it's often in convention. Like, you notice how we talked about different types of functions when we lump them into buckets, right? So for example, if you're trying to express a big O, and say you said, oh, it's big O of, say, 2n. One thing I want to make a remark about is that, as we know, constant multiplicative factors like this are redundant in terms of big O. So very often when people write things like this, they actually should, probably a much cleaner way of writing it is just to write big O of n instead. But I must stress, it depends on what you're actually trying to accomplish. If I'm just trying to express the running time of an algorithm, the latter is much more preferable than the former. The only time, one of the bigger situations where you might put more inside the complexity function is if there's multiple variables that involve the input, or there may be a constant that's relevant to the input size, but maybe not directly. It might be something relevant if, say, you're wanting to do something practically speaking. Sometimes these things might be relevant to it, keep in the big O notation, but if you're just interested in the input size in relation to how it grows, or we want to just measure the time complexity with respect to the input size, just what I have here on the right is perfectly fine. In fact, that would be usually what I encourage you to write. If, say, you run into a case where you're writing, oh, what's the worst case time complexity of the algorithm? You usually just want to go with this one as opposed to that. But anyways, I thought it would be a good idea I talk about some properties that big O has. Now, some of them I've included a proof for at least one of these in the notes, but I'll give you a flavor for how you would go about the proofs for these if you're curious about it. But I'm going to walk through some properties here. I'll give you a couple examples for some of them that aren't necessarily as straightforward. So the first thing is that if I give you three complexity functions, f, g, and h, and I have these three functions, these are three arbitrary complexity functions. So I'm going to go through four properties that big O has. There's more than just this. And of course, like CS210, you'd see more than just these. But I feel like I want to just give you a flavor for these kinds of properties you have. They often serve as nice shortcuts if you find yourself just needing to go from one step to another, just more broadly. Now, this isn't the exact same as just me saying, oh, prove it using the definition of big O. These are properties you can just straight up invoke. So for example, the first one here is the transitive property for big O. It works as follows. So if I know f is big O of g and g is big O of h, that means that both of these statements are true. Then I can say that f is big O of h. So for example, suppose f is n, g is n squared, and h is n cubed. What this is saying is, keep in mind that you can prove that f is big O of g here because n is big O of n squared. Likewise, you could prove that n squared is at big O of n cubed, right? So what this is saying, this transitive property is saying, what it's saying is if you had, say, for example, these three functions, what you could conclude is that n is big O of n cubed. You cut out the middleman in this whole process. Yeah, you can think about it almost like a sandwich. Yes. In fact, if you ever were to try to figure out how to prove this using the definition of big O, the way it works is that it's more like a one-sided sandwich, where what you do is you come up with a constant. It's actually very similar to the example I actually have in the notes that you're gonna, if you are curious about it, you can take a look at that. The proof is very similar to that one. And the idea is that you take and you combine the constants that you get actually from these. But I must stress that it's not necessarily a sandwich. It's more of a one. What it's saying is I can say something about f in relation to h by cutting out g. So the idea is I'm skipping over g here. So I can say something about f and h without having to talk about g. So sometimes this is helpful if you prove something involving g and h, but it's not so easy to prove it for, say, f and h directly. So sometimes this can be rather helpful. My example, maybe not so much, but most certainly it gives you a nice way of quickly jumping from one complexity function and just talking about big O for another one without having to take some extra steps if you already know a couple of facts on hand. So that's the first property I wanted to bring up to you. So yeah, I wouldn't necessarily call it a sandwich-like theorem, but it most certainly has some characteristics of what you might try to do if you looked at one side of the sandwich idea that you may have seen in like a course like calculus. But most certainly it's not, we're not sandwiching G in the sense that we're interested in F and H, but yes, G gets sandwiched in between the two. But the thing is, it's just that G becomes redundant in this whole process. That's why we call it the transitive, or we call it transitivity. This is a nice property that a lot of functions have, and big O is no exception. Or there's a lot of different mathematical objects that have this transitive property. But not all of them do. Big O does, though. So the next one, I think this one's a rather straightforward one, is that if I know that f is big O of g, and I give you some positive real constant, c. Now, I must stress that this c is not the same as the c in the definition of big O. This is just some other constant. Then what I can do is if I multiply this constant by f, I can also show that that is big O of g. The easy way of seeing this is that if you actually try to pull out the definition of big O, well, if you take a look at it, remember, in the big O definition, we have to find c and n 0, right? If I make f c times bigger, whatever the output is, all I need to do is incorporate that into a new constant that's based on the old one for this claim right here. I take that one, and I just make it, I can just scale the right-hand side up by c as well, because it's a constant, right? I'll let you think about that. So this is actually one form of one of the simple rules I gave you the other day. So notice that if you look at this just from another direction, what it's saying is that if you have a multiplicative constant in front of this here, it really doesn't make any difference, right? That's really what it's saying. Now, the third one here is just simply if I have two complexity functions and I show you that they both are big O of h, that means if I add the two together, then it's still big O of h. So actually, we seen a manifestation of this actually the other day when I was doing that example of using big O. For example, suppose that I have f being, let's say it's n squared plus 1000 n, and suppose that g is say, let's go with n cubed plus 3000 n squared. And suppose that h is simply just n cubed. What this is saying is that if I take n cubed plus 3000 n squared plus n squared plus 100n, the combination of both of them together, it will still be big O of n cubed. Because you can prove that f and g, both of these are big O of n cubed. So what this is saying is that if I sum these two, that's big O of n cubed. So this actually manifests itself as actually something very similar that we talked about the other day. That very simple rule I gave you about how we pick the most dominant term. Notice that the presumption I make about the most dominant term happens to be h. Notice that that's the thing I guess what the big O is, right? So if I just pick the most dominant term, notice I have a squared, an n, I have a cubed, and a squared, right? So if I just presume that h is something like a cubic function, then that's just like the second rule I gave you the other day. Does everybody see that? So you could generalize this to multiple terms, and you just take the most dominant term. Now, like I said the last day, remember, these terms, there's some constant number of the terms. It's not just like some infinite sum. You have to be very careful about those kinds of things. But that's the third property. Are there any questions about these first three so far? Or are they doing, are these clear? I think they're pretty neat, but they're also some handy, they're handy ideas that are related to some of the things I talked about the other day. The third. Yeah, so what's your question about the third one? If the sum gets bigger than h, is that possible? So this is the thing that I mentioned, is that if I give you f and I give you g, the thing that keeps this from happening, where can it be that the sum of them gets bigger than h? I understand exactly what you mean, though. Notice that it has to be that f is big O of h and g is also big O of h. So remember, both of these have to be satisfied. And you might say, Dan, how do you make sure that that isn't going to, how do you ensure that if I add the two, it doesn't become much bigger than this? Well, think of it. If I add the two, suppose that in here I have a constant c1 and I have a constant c2, and this has an n1 and an n2 for those two integers. So if I have two pairs of constants, the idea is that if you figure out which of the two is actually going to be bigger for a given value of n, well, all you have to do is just presume the other one is the smaller of the two, and you could just simply take whatever would be the larger of the two outcomes. So if you might ask, okay, so how do you know it gets bigger? Well, the first thing is that we know that this is in fact the case. But the other thing is just that, remember, it's because f is big O of h and g is big O of h. They can't erratically go beyond that if you add the two because they're both capped off at h. Now, if you're curious about this, I can I actually have the proof. Why don't we go through the proof then? So would people be interested in me going through the proof for the third property? I was going to originally ask you to take a peek at it, but I most certainly am happy to go through it if you're curious about it. So give me two thumbs up if you're curious about the proof for it. It's very simple. It's just that it actually illustrates a nice idea about the definition of big O. Okay, great. So I'll quickly mention the fourth one. It involves limits. The one thing that's handy is that if you know that if you can evaluate this limit, so if I have f and g, if I can take the quotient of these two and I take the limit as n approaches infinity of that function, it's not equal to infinity, then you can conclude that f is big O of g. So if you find yourself very handy with computing limits, keep in mind, remember that limit has to, in fact, be something you can actually compute. So if you can do that, you can actually establish big O claims that way as well. But I must stress that that isn't the definition of big O I gave you. But there's some caveats as well, but I'm just trying to keep it simple for us. Some people call this the limit theorem for big O. There's actually a much more general version of this that involves other asymptotic notations I'm not going to discuss here in this course. But yeah, so these are four properties. I'll give you a proof for property number 3, because it seems like people are interested in that. So actually, it's a nice way for me to quickly illustrate how we can use the definition of big O to prove a big O property like this. You'll find it's really, really nice. I must stress that property number 4, I'm not going to evaluate you on property number 4. So that's something I'm just giving you if you want to quickly calculate that off to the side, but I will not assess you on it. I just like to bring it up because it's something handy if you find yourself really especially if you got really cozy with limits from a calculus class. It's an easy way offhand to check. So here's the claim. So I'm going to try proving property number 3. So the claim is property number 3. Just for the sake of being abbreviated, I'll just write the claim is number 3. So I'm going to prove this for you now. So we prove this using the definition of big O. So I'm just going to pull out the definition of big O to do this. At first, this will seem a little bit strange because this claim involves statements of big O. But here's the neat thing. Do you remember in the statement it says F is big O of H and G is big O of H, right? These are both going to be presumed to be true. So if I give you a conditional statement like this, if both of those are satisfied, my goal is to establish that whatever follows from that, the then part of the conditional statement follows from that. So when I'm going to prove this, I'm going to presume that F is big O of H and G is big O of H. So here's the neat thing. We know what that means, right? We know we have a definition for that. So I'm just going to use the definition, right? So the whole idea is I'm going to take the definition, I'm going to pull it apart, and I'm going to try to build a new set of constants so that I could prove the then part, the part that says that F plus G is big O of H. So watch this. Since F is big O of H, there exists C1. So I'm just going to give them somewhat different names just because I'm going to have 2 of them. I'm going to call it C1, which is a positive real number, and I'm going to have N1. So that's N0, but I'm just going to give it a different name to make it easier for us to come up with our own C and N0 for this claim. Such that F of n is less than or equal to C1 times H of n for all n greater or equal to N1. Right? That's what F is big O of H means, right? So now all I'm going to do is just write what G is big O of H means. Also, G is big O of H. I'll write is big O of H. So there exists C2, which is a positive real number. Like I said, I'm going to just give them somewhat different names to make it easier so I can combine them in a special way to make C and N0, as in our definition of big O. I have C2 and N2. N2 is going to be a positive integer, such that the G of n is less than or equal to C2 times H of n for all n greater or equal to N2. So notice all I'm doing is using the definition of big O. Since I know these 2 things, I'm just writing out them, and as a bonus from this, I get constants out of it. They kind of just fall right out of the definition. So I'm going to now collect up those things I just dumped out, those constants, and I'm going to try using them. So now this is where you're going to see that this is actually going to be one of the times where I'm actually going to pick N0 first. You're going to see why in a moment. So let N0 be equal to the max of N1 and N2. So I'm just going to take N0 to be the maximum of N1 and N2. You might ask, Dan, why would you take the maximum of these 2 things? Well, I'll give you the insight or the idea I have. So we know that this inequality, G is less or equal to C2 times H of n, that holds for all n greater or equal to N2, right? And we know this inequality, F of n is less or equal to C1 times H of n, is true for all n greater or equal to N1. Do you remember what I told you about the selection of that integer constant? I told you that as long as you pick that constant such that it is at that earliest point where that trade-off happens, or crossover where one function dominates the other, or after. The after part is what's important here. So if I make n0 be bigger, the bigger of these two things, notice that because this statement is true for all n greater or equal to n2, for example, if n1 is bigger, that means it's still this inequality is going to still be true, even if I pick n0 to be bigger than n2, right? Because it's true for a value that is less than n0 and up. So watch this. So I'm going to use this fact to just ensure that this inequality and this inequality are both going to be true at the same time. So watch me kind of stitch these two inequalities together. So watch this. Then f of n plus g of n is less than or equal. So what I'm going to do is I'm just going to sum over these two inequalities, just like the bucketing trick I showed you the other day. So you notice how I'm just going to take f of n. I know f of n is less than or equal to c1 times h of n, right? And I know g of n is less than or equal to c2 times h of n. So I'm just going to sum these two together, and I'm going to write what's on the right-hand side of each one of these inequalities, just like I did last day with our examples. So watch this. So now I get c1 times h of n, and I have c2 times h of n. But notice I can factor h here because they're common amongst both of these. So that's equal to c1 plus c2 times h of n. But here's the thing. Because of the way I picked n0, I know that this will have to hold for all n greater or equal to n0. Which holds true for all n greater or equal to n0, right? So, question, what should c be? Any ideas what I should pick c to be? So what should c be? And remember, notice, yeah, you see it right here, right? Exactly. Does everybody see that? Notice that I've created a new c out of the other two constants, right here. So notice if I make c equal to c1 plus c2, notice that if I wrote a c right here, you'd see right away that this is just the definition of big O, right? Choose c to be c1 plus c2, then f of n plus g of n is less than or equal to c times h of n for all n greater or equal to n0 as desired. So since I've already brought up that I'm going to be using the definition of big O, I'm done. So I can say therefore property 3 holds. And we're done. So you might ask, so to answer your question about, well, how do you ensure that it doesn't get bigger than h? Well, here's the thing. Notice that the definition of big O gives me these two constants, and I can invent a new constant that is going to be just the sum of those two constants, because I'm just going to sum over them. And this will be big enough because I can pick an appropriate n0 that's going to be the larger of the two. So hopefully that addresses your question. I think that's a perfect way for me to address that. It's very much a good why question of why it would be possible. So are there any questions about this proof? So notice the key thing I did here. All I did was I used the definition of big O, and I used my premises that I have. So in this case, I know that f is big O of h, and I know that g is big O of h. So I just used those facts to derive my constants. So a lot of the properties I gave you in that list, for example, the transitive property, its proof is actually very similar to this one. That's why I didn't do it here. So are there any other questions about this? Because I want to move on to a new topic. New topic. Okay, so if we're good with this, that's all I have to say about big O at this stage. I may sprinkle every once in a blue moon something interesting about analysis of algorithms and relating to big O, possibly. But most certainly, that's most of what I have to say about big O. So we're going to go away from talking about complexity functions for a bit, and we're going to focus on another way of thinking about problem solving. So that brings me to the topic of recursion. Now, I like to usually get a feel for where everybody is at. How many of you have never heard of recursion before? I know that maybe some of you may have heard of it. Others may have never heard of this concept before. So like, give me a thumbs up or something. Let me know. Or give me any kind of fun sign you like. It usually gives me a flavor for this. Okay. Gotcha. Yeah, I got you. Okay, that's what I was feeling like. Some know about it, some don't. That's okay. That's okay. I'm going to start right at the basics of recursion, and we're going to work our way through, and we're going to see how we could solve different problems using recursion in this course. So we're going to actually see several kinds of recursive algorithms, so-called recursive algorithms in this class. It's going to be a very powerful way to describe and solve problems. So it's not just that, but also will pop up every once in a while when we talk about analysis of algorithms too. So the first thing you need to know about recursion is just a way of defining a function in terms of its own definition. It's what we call self-referential. So for example, somebody asks you what the definition of recursion is. Okay, well, the recursion's definition is just simply going to be that it's recursed amongst itself. Okay, well, what does that mean? Okay, well, then it's just simply defined in terms of itself over and over again. That's one way you can define it, but most certainly that has its flaws. But the point is that we're going to use the fact that we can re-describe a problem, in particular its solution, its algorithm, in a way that we can describe its answer, the algorithm itself, in terms of itself. So I'm going to go into detail about what I mean by this. So in programming, the way this will work is that if you have a function, what the function will do is call a function of the same name within it. So it's just going to call its own function again, but within it, which is going to sound at first very strange because you're used to it where if you write a function in, say, in C++, you're used to it, oh, if I have to call another function, I use that, right? But we're not used to often the idea that, oh yeah, the function is actually the exact same named function. So at first that sounds a little bit strange, but I'm hoping that I'll be able to demystify this and show you that actually this isn't really anything too special. It's actually just ingrained nicely into the notion of a function. So the big things I want you to take from our discussion, at least here today, we'll talk more about recursion probably on Monday, is I want you to start thinking about the idea of how we can describe how we could solve a problem in terms of the solution, but the solution is actually described in terms of smaller solutions, which at first sounds really strange. If you've never thought about this, I totally can get you. It's something that will build a kind of a tool set of thinking about how we can do this. We'll see some examples of how we can achieve this throughout this course. So the first thing that you want to be aware of is that it's very natural to describe algorithms recursively sometimes. In fact, you've seen some algorithms actually in 115 that actually would fit perfectly into my description. For example, you may have seen the algorithm called binary search before. How many of you have seen binary search before? Yeah, I most certainly would believe that many of you have. So this is in contrast to linear search. Binary search is much more efficient than linear search is, but it only can be applied in very specific circumstances, which we will talk about binary search here again, but I'll talk about it from a recursive standpoint so that we get a flavor for this. That'll actually be the first place we're really going to start after I get into some basic examples. We'll see binary search, but we'll revisit it from a recursive standpoint. Because I think when you peel it open, it actually makes it a lot easier to understand what's going on underneath the hood when you actually look at its iterative counterpart, the one that you've probably seen in 115. So let's talk about this. So the big thing is that if an algorithm uses recursion, we call that a recursive algorithm. So what does that mean? It means it calls a function of the same name. So that means that the idea is very simple. Is that I give you a description of my algorithm. You'll find that I'll call the function within itself, but remember, it's just a function call. The first thing that students make the mistake of is assuming that recursion just operates on a completely different level than other function calls. It's still the same idea, and I'm going to convince you of this fact over this lecture and next lecture. So at first, when you see it, just because it's not something you've seen before, it sounds a little bit more daunting, but I believe it's actually quite natural to do. In fact, it often makes it easier or simpler, or possibly simple. It's often simple to describe the algorithms recursively. And so it's also a mechanism for easily communicating the algorithms too. So just remember, it's just defining functions in terms of their own definition. That's the big thing for us. So the two things I really want you to notice is that whenever I design a recursive algorithm for you, there's going to be two key parts. And it's really going to be big for you to figure out and identify these two things. So every time we do one of these examples, I'll very often ask you, what's the recursive part? What's the non-recursive part? Or what I'll refer to as the recursive case and the base case. So what is the recursive case? So if I imagine I'm trying to solve my problem, there's going to be a part that's going to employ a recursive call. It's just going to call a function of the same name, but it's going to describe the solution to the answer in terms of a smaller version of the problem. I haven't yet really defined what smaller means, but I'm hoping with my examples I'll give you a motivation for what I mean by smaller, because I have to keep it overall quite broad, because this approach of describing and solving problems is extremely general. Just as general as the kind of stuff you've been working with before. So in fact, some would argue that it's like a more, I don't know, an orthodox way of looking at computation. There was a time where people were really obsessed with thinking about problems recursively and describing functions in a purely recursive manner. This is something that was like really popular, especially decades ago. And it's still something that you'll find niche communities are really obsessed with this kind of stuff. So the big thing is that we will have these so-called recursive calls, and they're just going to be applied to the smaller input. So when I talk about this smaller notion, I'm just usually going to be cleaving up the problem and making it in smaller chunks, or I'll be actually calling it on a part of the input that is, you can imagine like I made it smaller. So that's a recursive case. Usually you have at least one of these, but the base case is actually a way to solve the problem without using any recursion. So it's actually as presented. And we call it the base case is because when you take the recursive case combined with a small enough sized instance, you actually have a complete definition of how you can solve the problem. So here's the idea. Just describes the problem in a direct way of how to solve it. But the intuition here is that typically it's a small enough problem instance. And the idea, the big thing, is it just isn't in reference to anything else. So it's not going to be, without reference to itself, to be a bit more precise. So remember, it's not recursive, this base case. It's actually going to describe literally how to solve the problem with this one case. And in fact, you can have several base cases, as we're going to see. But the big thing, to make it easy to delineate between these two, is it has no recursive calls. Sometimes it's explicitly written out, other times it's implicit. So I want you to keep an eye out for these two cases as we start exploring this topic. So I thought before we really get into this knee-high deep into thinking about recursion, I thought I would do an example with you. So I brought my whole gang here with me to talk about how we can think about counting. So the first thing you might think of trying to do is if I'm trying to count. What's the first thing you might do? Imagine you have your friends here, all listed out, and say you want to know how many friends you have. Does anybody have any ideas of how I could count them? So imagine you're like hanging out with your friends and like, I want to count all my friends. What's an easy way for me to do that? So think of something you might try to do with some of the mechanisms that you currently have. So note, I'm not going to be overly specific about it. Yeah, add them up by one, right? You just simply just count. So you could just go through each one of them. So imagine I have like a clipboard. I can count a tally, right? I could just check them scanning from left to right, and I could just keep a tally. I can make ticks for myself to keep track of this information, right? And that's what you do, for example, with a for loop. And likewise, of course, you could do it in several other ways, but that's one way you could count your friends, right? Now, you might ask, okay, so what would I call that? So that's, for example, an iterative way of me counting my friends. So this is naturally described by things like for loops and while loops. Now you might ask, okay, so how can I describe counting in a way that the process is described amongst itself? So what the idea is that I'm going to describe to you how I can count my friends in a way that refers to me counting my friends, but doing it recursively. So here's an idea. I'm going to start at my leftmost friend, and what I'm going to do is I'm going to ask my friend if they have a friend to their immediate right. If there's a friend to their immediate right, they're going to ask their friend to the immediate right, how many friends are there to their right? So if you think of it like that, it almost sounds like I'm being really lazy, right? It sounds like I'm just being like, yeah, I'm going to pass the buck on to my buddies over here. I'm just going to trust that they are able to do this. So that's often one common thing that you have to get used to when you think about problems recursively, is that when I define my solution to the problem, I describe it in terms of myself. So when I talk about counting my friends, I'm going to count. So if I want to count my friends, there's myself and all my friends to my right. So if I ask my friend to the right, hey, how many friends are there to your right? And how many friends are there? Well, it's very easy to answer this question. So if my lion friend asked this question to my friend to my right, the dinosaur over here, lovely, lovely dinosaur. Well, what the dinosaur can do is the dinosaur can ask their friends to the right. Well, immediately their friend to the immediate right is ask, how many friends are there? Well, I asked my lovely cowboy friend, okay, well, how many friends are there to your right? Okay, well, they can ask the car here. Okay, now the car is going to ask their friend to the right. Well, I have a lovely green friend here. Well, my lovely green friend doesn't have any friends to their right, right? So all the friend can do is say, okay, well, there's no friends to my right, but there's me, right? So what my lovely green friend can do is tell the car, hey, look, there's one friend. There is just me. So the car says, hey, look, my lovely green friend told me, hey, look, there's only one friend to my right, but there's me, right? So I'm going to add one to that. So the cowboy gets back an answer and says, hey, look, how many friends are there to my right? Well, the car will tell them 2, right? So the cowboy will say, okay, I got 2 friends to my right, but there's me, right? So I'm going to tell the dinosaur. Don't ask me how the dinosaur understands this. I'm not quite sure about these things. The dinosaur gets the answer of 3 and says, okay, I have 3 friends to my right, but there's myself, right? So I add 1 to that. So I get 4 friends, and I can pass that along to the lion, and for which the lion will say, hey, look, all my friends to my right, they actually told me the answer was 4. In fact, all I had to do is ask my friend to the right here. And then I just add 1 to that, and I know that there's 5 friends. Do you notice in this entire process, I didn't actually have to pull out a clipboard or anything like that, right? Notice that I didn't take an overall view of everything. Instead, I described this process entirely in terms of counting, but counting friends to my immediate right. If I didn't have a friend to my right, I would just simply return myself, right? So there's really kind of 2 things going on here, right? So if I have a friend to my right, I ask how many friends are to your right, and you ask my friend to the right, right? But to ever get the answer, I just take whatever the result of that is, and I add 1 to it. Does everybody see that? So this is a different way of thinking about how I could count my friends. And keep in mind, it didn't have to necessarily be that I started on the leftmost over here. I could have started on the right here. And I could have just done it the other way around, where I start with my friend on the right here, and I ask, oh, how many friends are there to your left? And I could go through the same process. So this is just an example of how you could describe counting recursively. So notice that nowhere in this process did I ever just like simply say, I'm just going to go through all my friends and I'm just going to count them all. Instead, I relied on the fact that I could describe a very basic process to count my friends, but it entirely relates to the fact that I have one friend, and this one friend wants to know how many friends are off to the right. But I can always frame this in terms of asking my friend to the right to ask how many are on their right, and I can always get the answer by adding 1 to that. So somebody's asking, so this works for linked lists because the head won't know how many there are in the list. Well, yeah, you can adapt an idea like this for a linked list as well. That's one thing you can also do, but generally I'm just trying to give you a flavor for how we can think recursively as opposed to iteratively. So I want to give you just a recap of what we just discussed here. So let's talk about it. So we're going to do a few examples just so we get a flavor for this. So notice that the way I describe the answer that I get is always within terms of itself, but eventually I'm going to have to actually give you a direct answer, right? That's the purpose of the base case. So I can give you a complete description of how I can solve the problem. So you might ask, okay, so what is all this about? So suppose I go back to so I'm talking about counting here. So just to recap what I just talked about here, an iterative way of thinking about the example we just did would just simply to be the count through all your friends tallying up how many you found. Many you found and return the total count. So if you read this, you might first just think of this more like something that sounds like a for or a while loop. And if you have that intuition right away, that's good. That's good. That's where I'm going with this. Now, a recursive way. So rather than giving you a lengthy explanation of what I just described here, I'm just going to write it out in terms of the base case and the recursive case so that you can identify this process. So just to recap what I said over there. So here's a recursive way of thinking about this. So the recursive case is if there is a friend to your right, ask how many friends there are. So all you do is return this number plus 1. So you return whatever that number is and you add 1 to it. So the base case would just simply be that you have no more friends on your right, right? So otherwise, you return 1. So this is just for yourself because there's no friends to count, right? There's no more friends to count. So that's an iterative way of thinking about how you can count your friends. Here's a recursive way to count your friends. But notice the way I describe this is entirely based on the definition of counting in the first place, right? So if there's a friend to your right, ask how many friends there are. That's the recursive call. So you're going to see if you try playing around with this, that is in fact the recursive component of this. So let's think about this. So I thought I would do a couple of examples, just really kind of getting you cozy with this idea. Yeah, ask somebody's got their mic on. Can somebody mute their mic there? So I thought we would do some examples kind of walking through this mindset, like how we can reformulate something that we know how to do already in terms of recursion. So I thought we'd start off with something more basic. Let's just start off by counting numbers. So let's do that first. So let's head over here. Let's head over here. So one thing I'll mention while I'm erasing the board here is that recursion doesn't necessarily have to be where, oh yeah, you start at the bottom, just like my example here, I didn't have to necessarily start on the furthest left or on the furthest right. There's a lot of different ways you can think about reformulating a solution. You could count up, you can count down, you can, as long as the idea is that we're taking the problem we're interested in and we're trying to describe a way of solving it as a smaller version of itself. So I'm hoping I'll give you some examples of this. So we're going to definitely see plenty of examples just like that. Some that are a little bit more specialized than others. So I thought we would start off with just thinking about how we might sum terms. So let's do our first example here. It's just going to be, so imagine I want to compute a summation. So consider 1 plus 2 plus 3 plus all the way up to n. Now, you know a closed form expression for this, but for the sake of this exercise, I want to talk about how we can compute this iteratively, then recursively. So for example, actually, I have a question for you. Based on what we discussed about iteration or iterative approach versus recursive approach, can somebody tell me or suggest to me a way we could solve computing this sum iteratively? So think of something like a for loop or a while loop. Just keep it very brief. I'll probably understand what you mean. Yeah, so you'll probably have something involving a for loop, right? Where you're going to start it at probably 1 and you'll work your way up to n. And you'll just keep a running sum, right? So for example, here's an iterative way of thinking about how to do this. So I'm going to just straight up write this in C++ code, just because I think it's important that every once in a while we actually see some stuff like that. So here's a function. I'm going to make it so it returns int. So here's an iterative sum. So it has as a parameter n. And I'm going to have a running total. I'm going to call that variable sum. And then we're going to have a for loop. So I'm going to have for int I is assigned 1. I is less than or equal to n. I plus plus. And I'm just going to have it so sum gets assigned sum plus I. And that's the end of the for loop. And I just return whatever sum is, right? I'm sure you've done something just like this, or if not, something very similar to this before. So this would be an iterative approach. Now keep in mind that I would normally have this indented over here, but I'm just kind of running out of space over there. So do you notice what we did here? Notice that I add 1, then I add 2, then I add 3, then I add 4, then I add 5, then I add 6, all the way up to n, right? Well, let's start thinking about this recursively, akin to my example I had here. So let's think about this recursively. So let's think about this recursively. Now, I want you to, just for the sake of our discussion here, I want you to imagine that I want to compute that sum, but I'm going to start it at n. At n. I must stress that again, you could start this the other way around where you start this at 1. So imagine you start at n. My apologies. And now I want to compute this sum. Now imagine I'm given n. And I want to compute this entire sum, right? So you know that's going to be n plus n minus 1 plus n minus 2 all the way down to plus 1, right? Well, notice that if I want to compute the sum, notice it's just n plus all of this, right? Just all of that. Well, you could also describe that process over there, very similar to what I just did here. But what's this? This is just n minus 1 plus n minus 2 plus n minus 3 plus all the way down to plus 1. And you could do the same thing again. So you can say this is just n minus 2 plus n minus 3 plus all the way down to 1. Do you see how I can think about computing the sum almost like there's two groups going on here? You have whatever I'm currently adding plus everything else. Just like my example here where I was counting my friends, I took account for myself, but I also figured out how many friends I had by just simply consulting whatever would be over to my right. The same idea. So notice here that really I have two things I'm adding here, but the second thing is actually just a description of the same thing again, just it's one smaller, right? So notice that if this is the sum starting at n, this is actually just the sum of all the other terms less this one, right? So let me think about how we could do this. So let's write this out recursively. So I'm going to write it over here. So just keep in mind the idea that there's really just two things we're adding. We have whatever we're currently considering, and then there's everything else. But the point is that some point in this, we're going to eventually know how to add, say, for example, 1. We know what the result of just being 1 is versus 1 plus 2, right? But the point is I'm going to pass the buck over to the recursive call to do the rest of the work for me. For those that are not familiar with the phrase pass the buck, it just means I'm letting somebody else do that work for me so I don't have to. So here's a recursive way you could think about this. So first, remember that if I have n is equal to 1, I know the answer to this. It's actually just 1, right? So just keep that in mind. So here's how I can write this out in C++. So I can have int, and I'll have a recursive sum. It's going to take it as a parameter an integer n. And I'm just going to presume that n is a positive integer just because of the way I formulated it over here. So, as we talked about just a moment ago, you know the answer when n is equal to 1, right? You know it's actually just 1. So if n is equal to 1, then you could just simply return 1, right? So question, what of the two cases is this? What is that? It's the base case. So this is a base case. Just like when I run out of friends, the count on my right, that was the base case there. Otherwise, naturally, you can tell right away that if it hasn't gotten small enough, I'm going to have this recursive case. And it's just going to be like what I just described. So remember, I know what the answer is to the sum where I start off at n and I want to go down from n all the way down to 1. So I'm just going to pass the buck on to the recursive call. So to get my recursive algorithm, I'm just going to invoke a recursive call, which is just a function call, just like this. Watch. So I'm going to return n plus rec sum of n minus 1. And that's it. So to anybody, does this look really bizarre? Where it's actually just, like, notice it's the same name of the function here. Same signature. I just made the problem smaller, right? So notion here is that I have n, and I'm just going to sum up all of the other terms. So I'm just passing the buck on to this recursive sum to take care of that for me. So I'm entrusted that this is actually going to function properly. So I'm just trusting the recursion to do its job, because if you think about this carefully, just to remind you of what's actually happening, is I'm going to walk through what we did here and just show you it's the exact same thing I have over there. So suppose that n is equal to 4, just for the sake of discussion. So if n is equal to 4, you know it's not equal to 1, so it does this else call here. So it's going to execute this block. It's going to be n plus the recursive sum of n minus 1. So you know it's going to first call, it's going to be given, so we want to do 4 plus, so we're going to have 4 plus rec sum of 3, right? So this is just a function call. To compute rec sum, I'm going to now call rec sum. And now n is not equal to 1 yet. So I just go to the else block. I have it being 3 plus rec sum of whatever that number is, minus 1. 2. And to compute this, remember, it's just a function call. It's just the same one. But the thing, there's a couple little novelties here or there that I want you to be wary of when we get there. Is that when I compute rec sum, this is just 2 plus rec sum of 1. But here's the thing. This is just going to call, when this gets called, it's just going to be when n is equal to 1, so you know the answer is just 1, right? So, once you have the answer for this, you know it's 1 plus 2, that's 3, right? So all of this, the answer is 3. I could give this back now, seeing as it actually returns an integer, right? So it returns that, just like if this was a return value of any other function. So notice that I have 3 gets returned here, so it's 3 plus 3 is 6. So 6 gets returned right here. So I have 6 plus 4, that's 10. And that'll be what gets returned at the end. Now, I'm not going to yet get into the details of how the recursion actually gets executed. The point here is that we're really just doing the same thing I wrote over there, right? That's the big thing, is that there's really two terms here. Whatever I'm currently considering, and then it minus 1, I want to add up all the remaining terms. The recursive call takes care of all of that. So are there any questions about this example? Any at all? Don't be shy. It can be about anything about whatever's going on over here. I must stress that we're going to see plenty of examples. So don't worry if this at first is looking a little bit alien. I assure you, it's nothing about this is alien. Everything you know about functions is just as applicable here. So here I'm computing a sum so it's 1 plus 2 plus 3 plus 4 plus 5 all the way up to plus n. So what I've chosen to do is I started off at n and I'm counting downwards. So I have n plus whatever the sum is of the remaining terms. I must stress that in fact, I encourage you, if you want to give it a try rewriting this so that it starts off at 1 and it counts up to n. That's another thing you can also do, but I assure you that this way is a lot more natural because notice that my parameter is n and I can always decrement it. But I must stress that you can always have it where you call this on rec sum of 1 and then you just have it where instead of having it where you check when its n is equal to 1, you would just check when it's actually equal to whatever the upper value would be. But note in that case, you would have to reformulate this a little bit. But yeah, I think that this is rather much more natural way of thinking about it. So if we're okay with this, I'm going to show you another example. Because I think it's important that it's more about just getting exposed to it. And then once we see some more examples, we'll actually see how recursion works. And it all really comes back to how functions work. So I thought I would show you another example. I know you'll see this one later on in the labs, but I like to show it. I think it's a good example. It follows a very similar pattern to the ones that we've seen so far. Here's another example. We're going to check out factorial now. So you may have heard of factorial before. So I'm going to define it this way for the sake of simplicity, but there's other definitions out there. For any positive integer n, define n factorial, so it's read as n factorial. N factorial as... Now, I'm going to give you a recursive way of thinking of factorial. You may know what factorial is as this follows. So you might know as n factorial being n factorial is equal to n times n minus 1 times n minus 2 times all the way down to 1. So that's one way to define factorial. I have a question for you. If you've seen this formula here, what would be the first instinct for you to try if you wanted to implement this iteratively? What's the first thing you'd try doing? So right now we're thinking iteratively before we get to recursive. Yeah, just use a for loop, right? You just start it off, you could always start at 1 and work your way this way, or you could start at n and then you could... The key thing is that you'll have a loop where you multiply whatever the result of the product is, and you'll just keep track of this. And then you just return the result when you're done. So it's very natural to write as a for loop. But I'm going to show you that you could think of the same idea I have here recursively. So here is a recursive definition now. So you can think of this as an iterative definition if you'd like. That's just for us here. But here's a recursive definition. So here's a recursive definition. Well, notice that when I do this product here, notice that just like my previous example, it's n times all of this, right? Just like if I had considered only n minus 1, it's n minus 1 times all of this, right? So I could actually characterize it this way too, using the mayonnaise. I could have n times n minus 1 factorial, right? For those that are familiar with factorial, you may be quite used to the idea that you could kind of unroll the factorial like this. So this happens if n is greater than 1. And you can always define 1 factorial to just be equal to 1. If n is equal to 1. So if you're thinking about this from the perspective that we are, what would you call this first one? The recursive case or the base case? Keep in mind that we're going to reformulate this as an algorithm. Yeah, this is the recursive case because notice that it's actually just defined entirely by factorial, right? So notice the compute this n factorial is actually entirely divided, it's n times a computation of a factorial is just 1 smaller. And naturally that leaves you the base case right here. So, just to give you an example of what I mean, well, 4 factorial, this is the same as me writing 4 times 3 factorial. But what's 3 factorial? Okay, well, what's 3 factorial? It is just simply 3 times 2 factorial, right? But what's 2 factorial? Well, that's 2 times 1 factorial. But what's 1 factorial? It's just 1, right? Do you see it's just like the example I just did a moment ago, except now instead of summing, we're multiplying. Does everybody see that? It's subtle but interesting. So if you wanted to calculate this out, it should be 24, I believe. So, let me write out some pseudocode for this. So let's write out some pseudocode for factorial. So rather than writing in C++, I'm going to write it in pseudocode. Just because you can see now that it's just a function call. That's all it is. It's just that we're using one of the same name, same signature, just with the exception that we're changing the input or the input parameters. Because we want to make it smaller. You might ask, Dan, why does it have to get smaller? Well, think of it. I ultimately want to define the answer to you, right? I want to ultimately have this thing terminate in finite time. If the input never gets smaller, you could think of it just like if I had an infinite loop, right? That's one way you could think about it. Likewise, mathematically speaking, using the mayonnaise or mustard, make a good sandwich. You can also think of it as if we lack a base case, we actually have an incomplete definition of the answer. So, for example, if I didn't have 1 factorial over there, I wouldn't necessarily know what the answer is when I eventually get past something like a positive integer and I start getting 0, -1, -2, -3. I'll just keep subtracting, right? Forever. So let me write out some pseudocode for factorial. So let's get our algorithm. I'm just gonna call it fact, just for the sake of abbreviation. Now, I'll write it like this. Positive integer. And note that my pseudocode, if you look at the notes after, I made it for non-negative integers, but that's okay. It will actually just be the same. Output will be n factorial. So here we go. So I'm going to write this out, and then we're going to identify the key parts, okay? So if n is greater than 1, then I'm going to return n times fact of n minus 1. Otherwise, I return 1. Because I know that 1 factorial is equal to 1. So here's some pseudocode. That's all it is. So what would this block of code be representing? Is this the recursive case or the base case? The one I have my finger pointing on. That's the base case. That's a base case. So that means naturally this is the recursive case. You know right away because it has a recursive call. Very good, very good. So one thing I do want to point out to you, and this is something, at first it sounds really incredible, but it's actually not very surprising, especially once you see how recursion actually works. So, well, first, it is actually quite amazing given that we could describe a couple different ways of solving the same problem just in two different mechanisms. This one being recursive, you can think of iteratively how to compute factorial. There are two different ways of writing an answer to computing at factorial, right? Believe it or not, there's a way to take any one of these recursive algorithms and translate it into an iterative version. Likewise, I could take any iterative algorithm that I have, like with loops, I could rewrite these things recursively. So you might ask, okay, so keep in mind that if there's something that you can accomplish with a recursion like this, with recursion, you can of course do it with iteration. Likewise, you can do things with iteration recursively as well. So you might ask, okay, how is that possible? First, I should be very clear that the translation from recursion to iteration sometimes does not translate very easily. For example, when we actually talk next day about how recursion actually works, you'll see that actually this recursive call is just a function call, right? You actually just exploit the fact that on your system, on a computer, the way functions are organized is using a certain data structure. Does anybody know what data structure that might be? So you may have heard of one of the data structures we talked about near the beginning of this course. We may have heard of it in the context of memory. Starts with an S. It's a stack, yes. So believe it or not, on your system, the way recursion works, it's just the same way any other function works. It uses the call stack, or what we call the stack. It uses the call stack or runtime stack. It uses the same mechanism. So the way it works is that all you would do is you'd create your own stack. You implement your own stack data structure and you incorporate that into the algorithm. So instead of actually calling recursion, you would actually simulate it using a stack. The other way around is, I guess the real question is really just the other way around. I'll let you think about it a bit. If you're curious about it, I could talk to you more about it. But for the sake of this course, I'm not going to go that deep. But most certainly, you should see that really, once we learn more about recursion, this should feel a little bit less alien. So just note that there's this idea of iteration versus recursion, or recursive approach. And we've seen kind of examples of both of these. So one last example, I'll give you one quick example, and I'll ask you to take a look in the notes how you might write out some pseudocode for it, is the Fibonacci numbers. Another classic example. Fibonacci numbers are fascinating. So this is a well-known sequence of numbers. It's defined, actually, you can define it recursively. So the way you can define it recursively is by having fib of n is going to be fib of n minus 1 plus fib of n minus 2. If n is greater than 2, where fib of 1 is equal to 1 and fib of 2 is equal to 1. So you can actually define these kind of functions recursively, and you could actually, based on what we've just described here, if I were to show you the recursive algorithm, which I will do next class, so I will write out the algorithm for computing the Fibonacci numbers the way I've defined it recursively. Question for you. This first part here, where n is greater than 2, is this the recursive case or the base case? If you think of it as an algorithm that you're going to compute. Yeah, it's recursive. So this first part here, you think of that as the recursive part. And then if naturally fib 1 and fib 2, those are your base cases. So here we actually have two base cases. So you can also rewrite them as just a single one, but most certainly they'll work perfectly fine. So when we come back next time, what we'll do is we'll play a little bit more around with the Fibonacci numbers. Then we'll talk more about how recursion works. And then we'll go from there. We'll probably study binary search. I think it's a good idea so you get to see how binary search works when you think of it recursively. So I'll say thank you very much and have yourself a beautiful day. I'll see you later.